Welcome back to the seminar, and it's my great pleasure to introduce today Fabio Toninelli from the Technical University of Vienna, and he will speak about an SPDE version of WASEP in dimension D larger or equal than 2. Thank you, Fabio, for the invitation.
Thanks, Claudio. Thanks to all the organizers of this multi-site seminar. I will show my face at the end of the talk if you want. Okay, so yes, so this is a joint work, ongoing joint work with Giuseppe Cannizzaro in Warwick, who will, I believe, speak at your seminar in a couple of weeks, and Massimiliano Gubinelli in Oxford. So it has link with ASEP, but it's kind of a continuous version of that. So let's see. And so the plan is to introduce this singular stochastic PDE. Actually, it's a class of PDEs. Maybe I will get to the end to a generalization of it, which is motivated by out of equilibrium statistical physics and in particular by driven diffusive systems. So I will give a bit of introduction to that, to the equation, where it comes from, etc. And then the main focus will be about large-scale behavior or infrared behavior. I will recall some predictions about these systems and what we can prove. And in one line, the type of results will be Gaussian, large-scale Gaussian behavior in dimension larger than 2, and there is also the result in dimension 2. Although in a slightly different spirit. Okay, let's start with the lattice. Okay, I guess this will be very well known to everyone, especially given the list of organizers. But still, I will spend 1 minute about the asymmetric exclusion process. So we want somehow to model driven diffusive systems. So you have to imagine particles interacting via, I don't know, collisions, some kind of interactions. So they are diffusing, hitting each other randomly, kind of. Plus, there is an external field, like, for instance, if the particles are charged, you can think of electric field. And this external field gives a preferred direction to the motion of the particles. And in the stationary regime, it will induce some macroscopic flow of particles, some electric current, for instance. Okay, so it's quite standard. There is a quite standard way to discretize this type of system, to describe it as a continuous time Markov chain on a discrete lattice, but still time is continuous. And this is the so-called asymmetric exclusion process, simple or not simple. Okay, so it goes as follows. You are, for instance, on the lattice ZD. You have particles on the lattice, at most one particle. This is exclusion, and then the dynamics is continuous time, Markov chain. When a particle is at X, wants to jump at Y, the rate of jump is 0 if Y is occupied, is exclusion, and is some function P of, say, X minus Y if the site Y is empty. And this P of X minus Y, say, so it's translation invariant, just depends on the difference, but in general, does not need to be nearest neighbor, so X minus Y does not need to be norm 1, and it does not need to be symmetric. So so P of X is not necessarily P of minus X. So in general, there is a drift, an asymmetry. If you look at the sum over Y of Y times P of Y, in general it's not 0, so it's some vector W in RD, which we interpret as a drift. This is a drift that the particle has when it is isolated from the others. Of course, if it's packed into many other particles, it's just stuck. Okay, so this is the asymmetry. And because of the asymmetry, the process is irreversible. Stationary measures are Bernoulli, IID Bernoulli. And the question is about large-scale behavioral fluctuation. So introduce the usual occupation variable eta. Eta xt is the indicator of having a particle at X at time t, and then look at the 2-point function, the correlation function in space-time. C of xt by translation invariance and by stationarity just depends on time difference and space difference. This is the covariance between the occupation variable at xt and the occupation variable at 0, 0. And the averages are taken in the stationary measure, or Bernoulli in this case, with particle density rho. Rho is some number between 0 and 1. Okay, so this is C of xt. In the symmetric case where the kernel P of x equals P of minus x, in particular, the drift is 0. And then this particle system behaves diffusively. So the C of xt for t and x large approximately behaves like a Gaussian kernel with some variance of order t. So it has this shape asymptotically. So this constant d actually should depend on rho, but okay, let's imagine that rho is fixed. This constant d is the diffusion coefficient of the system. And another way to interpret this formula is that correlations in space-time decay on some length scale, which is of order square root of t. Because if you look at this exponent, it becomes, the exponential becomes small as soon as x is much larger than square root of t. And this is the typical diffusive behavior. So this is for the normal, for the symmetric case. You have so-called normal diffusion. And the question is now what happens when you have asymmetry. The W in particular is not, say that W is not 0, the drift. And then the question is whether the system is still diffusive. So with whether one would still have a similar type of behavior with a d of order 1, or whether this d will actually depend on t and diverge as t goes to infinity, in which case we would talk about super diffusion. Okay, so this is condensed 2 slides condensed on ASEP. And now actually the focus of the talk will rather be on a sort of continuous version of ASEP. So instead of having a particle system, we have a stochastic PDE. It's an SPDE that was introduced in the 80s by Beijeren, Kutner and Spohn. Essentially, you should think that you replace the particle occupation by some continuous function phi of xt, where now space becomes continuous, and now this phi does not take values 0, 1, but take values in R. So you should not be worried by the fact that this particle density can be also negative, because you have to think of other fluctuations of particle density. So you have to imagine you have an average profile, average density of particles, and this phi is actually the fluctuations around this profile. So they can be both positive or negative. And now we have introduced an equation for this phi. By the way, let me say, this paper by Van Beeren, Kutner and Spohn is not really a rigorous derivation of this equation from ASEP. It's it's a heuristic derivation. Then they look at this equation for its own sake. So the equation looks as follows. It looks like this. You have a time derivative of the phi, which has three terms. There is the diffusion, the Laplacian phi, which mimics the diffusive behavior of the particles in the ASEP. Plus, there is this nonlinear term of the type W dot gradient of phi squared, which mimics the drift part. Plus, there is the noise in the form of divergence psi. So let me discuss it for a second. So let me call just this equation stochastic Burgers equation. In 1D would be the usual stochastic Burgers equation. So this noise has the following form. You take D independent white noises in space-time. Let me call them psi I from 1 to D. You take this as a vector, and then you take the divergence of this, and this defines the noise in the equation. And the reason it has this form is that you want to, microscopically, you want to preserve to conserve the number of particles. So you want a noise that is in divergence form. Okay, so this is the equation. Whether it can be obtained really as a limit of ASEP is another question that we will not discuss. Okay, good. So right. So and W is some vector in RD. Think of it as okay, not necessarily of norm 1. It's some vector in RD. Okay. Some features of this equation. Well, it's an SPDE, and it's quite singular. It's ill-posed in every dimension. So phi, you can, because of Gauss of the white noise, divergence of white noise type of noise of phi will be at best a distribution. Then here we take phi squared. It's a usual issue with singular SPDE. So as written, this equation doesn't make sense. So it needs to be regularized. Okay, this will come later. So the another observation is that if you set W to 0, so the nonlinearity disappears. And then if you start from a Gaussian initial condition, the space-time process is Gaussian because of linearity. Okay, and actually very easy to start. Another observation is that if you take d equal 1 and you look at the primitive of phi, so if you look at psi, so that dx psi is phi, then psi solves the one-dimensional KPZ equation. This is well known. But in dimension, as soon as dimension is larger than 1, there is not an obvious relation between this stochastic Burger's equation and the d-dimensional KPZ equation. Another observation is that, as you probably all know, singular SPDEs have witnessed a lot of very impressive activities in the last, I don't know, 20 years or so, or maybe less actually. What is known as high-res regularity structures and other pathwise methods are not designed to deal with such equations. Actually, they don't apply to this equation as soon as dimension is larger equal to 2. So somehow these methods are not designed for the large-scale analysis of the equation, but rather for the small-scale regularity study of the equations. So we'll be interested in large scale and in dimension be larger or equal than 2. So I'm not claiming that our methods are better than regularity structures. They are really designed to do different things. All right. So a first remark on another remark of the equation is that if you look at the linear one, it's diffusively scale invariant. So you take the linear equation. I've dropped the non-linearity. And then I do a diffusive rescaling like this. I take epsilon positive, and then I rescale the time and space diffusively, like in this green boxed formula, multiplied by epsilon to the minus d over 2. And then you just plug this phi epsilon into the equation, and you notice that this phi epsilon solves exactly the same equation. Well, I mean, the noise is not the same, but in low is still the space-time white noise. So in low, the linear equation is scale invariant under diffusive scaling. So, and then what one does is, well, let's take now the nonlinear equation. Let's do the same scaling and pretend that the equation has a solution and plug this phi epsilon into the equation, in the nonlinear equation. So what happens, at least formally, is that the linear parts stay invariant. I mean, this is what we have just seen. And the nonlinear part stays the same, except that it gets a prefactor which is epsilon to the d minus 2 over 2. Okay, good. So this rescaling suggests the following, that if you are in dimension larger than 2 and you look at large scales means epsilon small because of this rescaling here. Okay, so in dimension strictly larger than 2, then this prefactor will vanish for epsilon going to 0. So one expects somehow nonlinearity to be irrelevant, and asymptotically to recover the linear equation. So somehow, for instance, you expect the diffusion coefficient to be of order 1, like for the linear equation. For dimension smaller than 2, so meaning 1, this prefactor explodes for epsilon going to 0. So you expect super diffusion, most likely with, well, okay, now we know, with the diffusion coefficient that will explode like a power of time for large times. And in dimension 2, this prefactor is just 1, so some finer analysis is needed. This dimension 2 is called the marginal dimension for this equation. Okay. Now, well, of course, this is a purely formal argument. It assumes that the solution exists, but the question is, well, is it posed? But usually, this type of scaling arguments gives the correct answer. Another observation is that if you take this argument literally, you would expect that in dimension larger than 2, strictly larger than 2, this nonlinearity just disappears in the limit. But it's too naive to expect that on large scales, the equation will just converge somehow to the linear equation, period. So even in dimension larger than 3, larger than 2, larger equal than 3, we will see that the nonlinearity has a non-trivial effect in the large scale limit. Even though, so for discrete models, even though you cannot do this easily, this formal, this scaling argument, the same scenario is conjectured, and as I will comment in a moment, is actually largely proven. So there is a universality type of scenario where, this same type of conjecture of behavior is expected for discrete models in a quite large generality. A very cryptic comment about dimension 2. As I said, this is rather subtle. Whether you will have superdiffusion or not, you cannot be guessed just on these easy scaling arguments. It really depends. That really depends on finer issues like the symmetries of the models and so on. Okay, but we will not see this today. Okay, so this was very formal. So to give a meaning to the equation, there are several ways. So it's called, it's standard word is regularization. You have to first turn the equation into something that is well posed, and then start doing things. So there are at least two ways to regularize the equation. The first one is to smoothen the noise. The problem is not being delta correlated in time, but being delta correlated in space. So you would replace the white noises. Okay, we have to take the divergence of white noise, but let's look at the noise psi. Instead of having a Gaussian noise, which is delta correlated in space and time, you would replace it with something that is still delta correlated in time, but in space it would be what's called colored noise, where the correlation between psi x and psi y would decay with x minus y smoothly on some length scale a. Okay, this is one possibility. The second possibility is to leave the noise as it is, irregular, but to regularize the nonlinearity. And that means the following: phi squared is ill-posed. So what you do is you apply to it a regularization in Fourier space. This pi with index 1 over a means it's a projector in Fourier space that projects only on the Fourier modes on the k smaller than 1 over a. Okay, so it takes phi, it just keeps the modes k smaller than 1 over a. Then now it's very smooth function. You can square it, and now technically it's convenient to again project on the modes smaller than 1 over a, because if you take two functions with Fourier modes say smaller than 1, you multiply them, you can get Fourier modes up to 2, say. But then again, you project on these modes. Okay, so this is now a very well a legal operation. You take a function, you just have small modes. You can do whatever you want to it. You can square it or take the power 4. And so this defines the regularization of the nonlinearity. And a, what is a? This cutoff a can be thought of as a I don't know, some lattice spacing. For instance, you can think of a being 1. For ASEP would be the lattice spacing 1. Okay, so let's take a equal 1. But then, of course, then we are interested in somehow removing this kind of arbitrary cutoff. So somehow to removing this, to sending a to 0. But this is done automatically when you look at large scales, because suppose you define your equation regularized on scale a, and now now you do the same diffusive rescaling as before. What one can check easily is that this phi now rescaled diffusively on scale epsilon has a cutoff which is not anymore a, say 1, but a times epsilon. So this cutoff is disappearing, looking at larger and larger scales. Okay, so again, I take the equation, I regularize it by putting this cutoff a equal 1, but then since we will look anyway at large scales, it's as if this cutoff will disappear. Okay, as a remark, of course, the discrete models have a built-in cutoff. You don't need to regularize them. Okay, so I will write down again the equation in a moment. Let me comment on some known results. So in dimension 1, it's known that indeed the equation is super diffusive. So the diffusion coefficient d diverges like t to the power 1 over 3. There are many results. I will not even try to make a list. either on the equation itself or on particle systems. This is by now quite well understood. In dimension 2, that's more subtle. There was in this paper where Van Beijeren, Kutner, and Spohn introduced the equation, they also argued via so-called mode coupling theory that the diffusion coefficient should diverge like logarithm of t to the power 2/3. And in the case of the discrete model, the ASEP, in 2D, this was proven by Yao in 2004. As far as dimension 3 and higher is concerned, for the particle system, for the ASEP, the fact that indeed for large scales the model is diffusive and then there is a Gaussian scaling limit has also long history. I mentioned here some of the results of the key results. This Landim Yao paper by 97, then Chang Landim Olla and Landim Olla Varada, but there are others, and I would suggest for those interested to look at the Komorowski Landim Olla book for this. So in dimension, somehow the picture is rather well confirmed by now, but there are still some open challenges. First, one which is we will address today is can also so this last dot here was about dimension higher equal than 3, but for the particle system. Can one prove large scale diffusive behavior in high dimension also for the SPDE? Somehow we want to get a scaling limit for a singular SPDE, which in the language of SPDEs is so-called supercritical, and this, as far as we know, has not been done for other supercritical SPDEs. So this SPDE is motivated by ASEP, but technically it's quite different. It's quite different. You are trading a variable eta which has value 0, 1 with something unbounded, and this induces a lot of analytic difficulties, so need for renormalization, etc. So technically, it's of course it's quite different. And then another open challenge, well, by now maybe not entirely open, is about scaling limit in the marginal dimension d equal 2. In d equal 2, we have seen that there are some slight superdiffusivity, slight meaning logarithmic. Still, one would like to see some scaling limit, and this is open for ASEP, as far as I know, it's open. Okay, so let me come to a first result. So what we do is so this again with Giuseppe and Massimiliano, and it's being written down. We are in dimension at least 3. We look at our equation with regularization, and then we rescale diffusively. So we define phi epsilon as epsilon to the minus d over 2 times phi of t over epsilon squared, comma x over x. If you plug that into the original equation, here is the equation that you get, where as before so let's look at it again. You have the Laplacian, you have the divergence of the white noise, and then you have the non-linearity, which has the epsilon to the d minus 2 over 2 in front, has the regularization, it's written here in green, and the regularization is again a Fourier regularization where you project on Fourier modes smaller than 1 over epsilon, 1 over epsilon because of this rescaling, the cutoff on scale 1 becomes 1 over epsilon. And then let me take W a vector in Rd of norm 1, and let me put out the norm and call it lambda. So so it's just a choice. I could have called lambda W, could have called it W, but I prefer to do it like this. Okay, so this is the equation we look at. And something I forgot to say is that the same way as for ASEP, the stationary measures are Bernoullis are stationary time stationary measures. For this equation here, the white noise in space is stationary. So if you and actually all our theorems concern the stationary process. We start at time 0 with a white noise in Rd, and that's at all times you take a picture of your solution. It's distributed according to a white noise. So there is no, but then the question is about the space-time process. Okay, so what the theorem says is that, let me have a look at the watch, yes. What the theorem says is that as epsilon goes to 0, the solution of this equation converges to the solution of some process, let me call psi, this limit process. Psi is a solution of a linear parabolic SPDE, which looks as follows. This is a limit equation that looks as follows, like dt psi equals some effective, so okay, some L effective times psi plus a noise. Now, the original linear equation where you just dropped the nonlinearity was of this form, with L effective just the Laplacian over 2 and eta being the divergence of the white noise. So this new operator L effective is not just the Laplacian. So as I said before, even in a good situation where in a high dimension, you cannot expect that on large scales the nonlinearity just disappears. I mean, it leaves some trace, and in fact, this L effective is the sum of the old linear operator Laplacian plus something new, and this something new is in the form of a constant depending on lambda, which is positive as soon as lambda is not 0, times a differential operator, which, like the Laplacian, is second order, but it's not a Laplacian. It's like a Laplacian, but in the direction of the asymmetry. So it's W dot gradient squared. Okay, so so if you want, in Fourier space, this effective operator is minus k squared over 2 minus this W dot k squared. Okay, whatever. So important is that this C of lambda is simply positive. So there is a non-trivial effect as soon of nonlinearity in the limit. The noise, I will not write it down explicitly, but it's easy to guess in the sense that since the equation admits since the white noise in space has to be stationary, then this noise will be simply a Gaussian centered noise that is most easily described in Fourier space. If you take the component k of the noise, let me call it eta hat k, then the components are, well, in a sense, independent. Well, okay, so the components are independent, and the variance of the component eta k is just k squared. That would be the white noise. Well, the divergence of the white noise, plus this extra term, this C lambda W dot k squared. So this is just to say that the noise is different, but it's what you would guess if you knew, well, if we know that the equation preserves still the same white noise as the original equation, as the linear equation. Okay, so somehow once you give the L effective, the form of the noise is constrained. Okay, this C of lambda is not really explicit. You can prove several things, bounds, and in a sense a certain representation formula, but it's not something like lambda squared over pi. Okay, so at the end, I would like to spend maybe 10 minutes explaining a bit the idea of the proof. But before doing that, assuming there are no questions, let me also give a result about the two-dimensional situation. So in the two-dimensional situation, we know that something goes wrong, meaning that if you don't do anything to the equation, you cannot expect a diffusive limit. Already the Gauss result for ASEP or the heuristic result by Spohn and collaborators for the SPDE show that something goes wrong, but not too much. I mean, for instance, the diffusion coefficient of this equation will explode logarithmically with epsilon with this power 2/3. So somehow you have to do something to the equation to tame this nonlinearity. So, and there are two possible ways of doing this. One way is similar to what you would do in particle system when you look at the weakly asymmetric regime like WASEP. Okay, the thing you could do, in fact, this is what will come in a slide, is you take your nonlinearity and you make, since it induces some exploding effect in the limit, you tune it down by multiplying by prefactor lambda epsilon, where this lambda epsilon goes to 0 as the scale epsilon, well, as the scale grows. So this lambda epsilon will go to 0 with epsilon in a suitable way that is fast enough to kill the explosion, but not too fast. Otherwise, you will not see anything interesting. Okay, this is what we'll do, will come in a slide. The other thing you could do, which would be, I think, even more interesting, is to take the equation as it is. You're not allowed to modify the equation, but what you are allowed to do is to take a scaling which is different from diffusivity. So you would take your equation and rescale time and space a bit differently than diffusively. So you would divide t not by epsilon squared, but by epsilon squared times a power of log, and then hope that with this new space-time rescaling, the equation would have a limit. This is something that we are not able to do right now. Okay, but this weak non-linearity limit is something we can do, and this gives the following work in progress result, again with the same quotas. So let me reformulate it precisely. So take d equal 2 and take the solution of this equation here, which is the same as before, except that this time the epsilon to the d minus 2 over 2 is just 1. And in addition, we multiply the nonlinearity by a prefactor that goes to 0 with epsilon in a precise way, proportional to the 1 over square root of log epsilon. The square root of log epsilon is suitably chosen. And then in this case, again, you have a scaling limit as epsilon goes to 0. And the limit is the same as before, except that now the C of lambda will be something different, but still a positive constant. So, but the limit will again be of this form here. Okay, so somehow I think this suggests. I don't know if anyone has looked at that. If you, yeah.
Fabio, I have a question.
Yes.
So
yeah.
You showed the a couple of slides ago that things should blow up like log to the 2/3 or something like that.
Yes.
And now you are divided by log to the 1/2.
Yeah, in fact, so it's a bit. Yeah, I agree. It's a bit surprising, but in fact, we expected we should have divided by log to the 2/3 or 1/3 or whatever. But maybe it's not that surprising. So if you think of KPZ in dimension 2, so there is the usual KPZ, and there is a so-called anisotropic KPZ. They have very different on large scales. They have a very different behavior. One has square root log t the super diffusivity. The other one, okay, no one knows, but most likely it's you have a super diffusivity which t to some power. But still, when you do this weak scaling limit for both of them, you have to take the 1 over square root of log weak scaling limit. So yeah, so I don't know if it answers the question, but yeah, it can look a bit puzzling, but this is the way it comes out. So
thank you.
You know, these results by I don't know Caravenna, Sun, Ziguras, they for the usual KPZ in dimension 2, they have to divide by square root of log n. And for the anisotropic KPZ, which on large scale has a totally different scaling, something we did with with Giuseppe and Dirk Gerhard. Again, we have to divide by the same square root of log n. So yeah, it's puzzling, but maybe not entirely. It's okay. Okay. So
thank you.
yeah. Okay. So there is still actually more time than I thought. So. Well, if there are any questions, so it can be a good moment. Otherwise, I would spend maybe 3 slides trying to explain at least the ideas of the proof of the first result, this one about d larger than 3, large equal than 3. Actually, so for the experts, so Claudio and many others, so, Milton, what can I say? It will, at this level of details, you will barely notice the difference with respect to what one would do with ASEP. Okay, now technically it's quite different, but at this level of sketch, it looks very similar. And in fact, we did import a lot of ideas and tricks from what was done for the ASEP before. I think one of the merits of the work is that of importing certain techniques and ideas in the SPDE world, which are known from in the interacting particle system, but which are kind of new in the SPDE world, where I think they have quite a lot of potential. Okay, suppose you want to prove our theorem. So you will start the usual way you do it with particle systems. So you take your solution phi epsilon, and then you integrate it against some test function f. Okay, it's called this phi epsilon t of f. And then you write the equation for this and you integrate the equation in time. Okay, and what you get is what you see in the first line. So you get phi epsilon t of f minus the same thing at time 0. Then this equals the integral from time 0 to time t of the right-hand side of the equation. So you get integral of phi epsilon of Laplacian f over 2. This is from the linear part. Minus, of course, the integral from 0 to t of the nonlinear part, which I just denote as n epsilon, just for simplicity. N epsilon is simply the nonlinearity of the equation, so the w lambda w dot gradient phi squared tested against f. Okay, compactly I just write n epsilon. Okay, so and the right-hand side is just the time integral of the noise, which is a martingale. The very explicit one is a Brownian motion with a certain covariance, variance, quadratic variation, which is just what is it, the H1 norm of f or something like this. So it's not some martingale which is completely explicit. Okay, so this is nothing. It's just integrating the equation from time 0 to time t. What we would like to have is that this, of course, the difficult part is this integral of the nonlinearity, and what we would like to recognize in it is the integral is that for epsilon going to 0, it is essentially given by a martingale part, which will modify the noise, will turn the noise from psi to eta, essentially, plus something else, which will be linear, and which will somehow modify the Laplacian into Laplacian plus what it has to be. So we would like to see that this integral is essentially integral of phi epsilon s tested against f to which you apply the additional part of this Laplacian L effective. Okay, so if we have this, then we are done. This is the usual way one starts. Okay, and then one starts looking at the generator. You have a Markov process, has a generator L epsilon. You decompose as usual into a symmetric and antisymmetric part with respect to the stationary measure, which is just a white noise. The symmetric part is essentially just the generator of the linear equation, and then you have the antisymmetric part that, of course, you can write as something minus something adjoint, the same thing adjoint. And then something that is very convenient. It's not okay. It's not totally necessary, but it's very convenient. Is that this antisymmetric part has a very simple, in a sense, structure. Okay, so this is maybe will be a bit quick, but this is something that happens also for the particle system. Something analogous happens. So the stationary measure is Gaussian. It's the white noise. So what you can do is to split L2 with respect to this measure into the so-called Wiener-Krauss decomposition. So you make an orthogonal decomposition where, say, H0, which is not written in this formula, would be just a constant function, constant random variables. H1 would be the functions which are linear in phi. H2 will be generated by Hermite polynomials of order 2, etc., etc. And it's something you can do in any Gaussian space. And then it so turns out that this asymmetric part of the generator has this particular form, that there is a part of it which we call A plus, which maps the nth Wiener-Krauss into Hn in the n plus first. So it's a kind of creation operator as it would be called in theoretical physics, and it's a joint that does exactly the opposite. So it's an annihilation operator. Strictly speaking, it's not essential that we the last slide about generalization, but it's quite convenient. Anyway, so this is not obvious, but you have to look at the generator, and it turns out to have this structure. And then what you would like to do is, okay, so remember, we have to look at treat somehow this integral from n0 to t of the nonlinearity. So the idea is to look at the so-called truncated generator equation. So you want the nonlinearity is given, and you want to solve this equation minus generator applied to some v, which v is the unknown, equals n. So you want to solve for v and find a solution of this. So in which sense it's truncated, because it's convenient to look at the generator where you project the generator on only the cows from order 2 on. So you cut away all the linear functions somehow. So it's a projection of the generator on only cows 2, 3, so and 4 and so on. And then okay, so suppose you can, okay, technically you have to do other things, but at the level of this sketch, this is what you have to imagine. So it does not really solve the so-called generator equation or Poisson equation, minus LV equals N, but there is this projection, okay? And then if you write the same equation, a similar equation with a full generator, L, without this larger equal to, then you have an extra term, okay? Because, okay, so if you look at the full generator L epsilon, then you have that this minus N will be L epsilon times V plus A plus star, which lowers the cows, applied to the second component of V. So you have to, you first solve the blue equation somehow. You take V2 is then the component of V in the second Wiener cows. You apply to it this A star plus, give something in the first cows, and then this combination is then this black equation. I don't know if you can see where I'm pointing. No, probably not. Anyway, this equation is then a consequence of the blue one. Okay, for the moment, I mean, why not? And then you go back to the integral. You have the integral of minus n epsilon computed at phi s epsilon ds, and then you replace this n by this as follows. Okay, so you have the sum of three things. You want somehow to remember what is our purpose, to write this integral in blue as a sum of a martingale plus something that will we recognize as a linear operator applied phi against linear operator applied to f plus something small, and this is exactly what we do. So we write this integral in sum of three terms. The first one is a martingale because it's the form integral from 0 to t of L applied to something minus this something at time t plus this something at time 0. This is a martingale. Will contribute to the noise. The second term is something that doesn't have a special meaning. Is this something that we have added to the first line, so we have to subtract it back, but it's something annoying, plus a third term. Okay, so this up to here we have just done manipulations. And now what will happen, and this is the crucial point, is that this solution V epsilon of the generator equation will have two properties. First of all, that as epsilon goes to 0, it will tend to 0 in L2. And this is good because then this second line, this term 2 is just negligible because it's the difference of such two V's, both go to 0. So this term is just disappearing in the limit. That's good. But that this V does not leave without leaving a trace in the world. That is, if you look now at this A star applied to V component 2, it does not go to 0. Actually converges to what we want to converge to. It converges to phi, to a linear function of phi, which is exactly what we want. Okay, so somehow I don't know, it's not so intuitive. So you have this V that in a sense disappears, but when you do something to it, in particular you apply to this annihilation operator, it gives something that has a link. Anyway, so this all the work, most of the work is in proving this. And if you believe this, then you go back to our formula here. Well, actually even to here, to the first formula in here. And what you would find is that asymptotically in the limit, you have that phi solves this particle problem. So you have that phi t of f minus phi 0 of f minus phi s tested against L effective applied to f is some martingale, which has an explicit quadratic variation. And this is exactly what will allow to say that phi in the limit solves the linear equation with L effective as elliptic as generators. So this type of decomposition, this type of approach is very similar in spirit to what Landim could, to the kind of fluctuation dissipation theorem result, for instance, for ASEP by Landim. So you want to decompose this nonlinearity as a sum of something you like, which is a linear, plus something that you don't necessarily like, but is of the form L applied to a function. And that will fluctuate fast in time and then doesn't give a contribution. So in spirit, as I say, it's quite similar, but technically, it's rather different. Okay, so this was the sketch of proof. My time is almost done, but still I would like to spend 2 minutes on a generalization. That is, okay, so this is again work in progress. In which we started with a very specific equation. This the linearity is given by W dot gradient of phi squared. But why phi squared? So in the original paper by Beijeren, Kutner and Spohn, they took this nonlinearity as the simplest one. It's like in KPZ. You put the gradient square because you think of some expansion of some nonlinear term, and the lowest order term is squared. But this equation with a square does not have a fundamental meaning in nature. So somehow it would be reassuring to find some results with more general nonlinearities. So this is what we are doing. So essentially, what we do is to study the same type of equation, but instead of having a nonlinearity of the type W dot gradient of phi square, we can take W dot gradient of some function of phi. For the moment, we can do the case where F is a polynomial or an arbitrary polynomial. So okay, I guess we could do a bit better, but this is what we can do for the moment. And again, one finds exactly the same type of results. So the limit equation is the same, just the constant C will be different. That's inevitable. And somehow this type of universality result is in spirit similar to what Harrer and Castell, or later Gubinelli and Perkowski, did for one-dimensional KPZ. So essentially, they took stochastic burgers, or KPZ in one dimension, and they show that when you take a nonlinearity of the type dxf, in the weak scaling limit, again you fall on the KPZ equation, where the nonlinearity is simply or the stochastic burgers equation, where the nonlinearity is dxu squared. Okay, it's a bit in the same spirit. There are some differences. For instance, in the Harrer-Castell result, what turns out is that if in a nonlinearity you decompose it, this f you write as a sum of Hermite polynomials. Only the second Hermite polynomials counts. In our case, all of them give a contribution. Well, anyway, but it's somehow in the same spirit. You want to replace this nonlinearity, this quadratic nonlinearity, which was chosen for simplicity, with something much more general. And yeah, I think I'm essentially done, and I should be on time. Thanks a lot.
Thank you. So we have time for questions. So maybe let me start. Thank you very much for this very nice talk, Fabio. So two questions. So how important is your regularization in this argument? So so is it extremely important, or could you think of other regularization and apply the same?
We could do the usual smoothing of noise in space. It's convenient somehow. Okay, yeah, we could do that. The advantage of what we do, I don't know how advantageous is this. One advantage of our regularization, maybe the only advantage, is that the stationary measure is independent of the cutoff. It's always a white noise. If you regularize the noise, instead you have a measure which depends on the cutoff. But okay, so that's it. There is not. We could do the regularization of the noise in space. Yeah. You have to preserve symmetries, but yeah.
Fine. And then in dimension 2, so yes, where the argument breaks down,
You first of all, you don't have tightness for the non-linearity. So, okay, there is as usual, there is a tightness part where you say, okay, you have tightness for the process, and then I want to identify the limit points. So a tightness fails in dimension 2 if you don't scale to 0 the non-linearity. So I would say it fails immediately. But it has to fail. So what is less easy? I mean, less easy. We cannot. What we cannot do is to show that if where is it? If we do in dimension 2, where if we don't scale to 0 non-linearity, but we scale differently time, that the process is tight. This I think we cannot do yet. By the way, maybe to make a connection with Milton's question before, if we do this second thing, I think, so I wrote on purpose alpha without writing what alpha is in this second formula, but in this case, I would think that indeed we have to take an alpha, which is something like 2/3, which is not the 1/2. But so I say, if we did not have weak scaling, but the modification of the diffusive scaling. So in this second approach, which we cannot do for the moment, I think that here you would see that alpha is not has a trace of these 2/3. But here I was a bit cautious, just wrote alpha. But I would guess that in that case, alpha has to be 2/3.
Right. Well, thanks. Any other questions?
So thank you, Fabio, for your talk. So you put WASEP on the title. So I was just curious if in dimension 2 this what you're mentioning works for WASEP.
It's not that we really tried, but for the it should work. It should be true. Yes, I mean the analogous result should be true. I'm pretty sure. Whether we are able to do it, I don't know. So Gauss result. I mean, Gauss result is upper and lower bounds for D, for the diffusion coefficient, and this is upper and lower bounds. There is a part where what he calls was also called before in the work with Claudio Castel and others, the removal of hardcore. So you want to replace somehow the generator with something where the hardcore constraints is removed. So there is some operation. So which works well if you do bounds. Whether this operation would fit well with actually getting a limit process is less clear. So short answer is I don't know. I expect the result to be true for ASEP, but technically it could be challenging.
Okay, thank you.
So any other question? Let's see. No questions on the chat. So, well, thank you very much, Fabio, for this talk.
Okay, thank you. So now you can see me.
Thank you.
Okay.
And, bye.
Bye. Thanks for the invitation again.
And we meet next week with Milton's talk. Okay. Bye-bye. Thank you.
Bye. Bye-bye.